Again, thank you very much for the opportunity. So as I was already introduced, I'm working in the company Nenovision. We are located in Brno, Czech Republic, and our main product is the small atomic force microscope module that can be easily implemented inside of the scanning electron microscope. And the product is called as LiteScope, and the current or the newest version is LiteScope 2.5 that was released around half a year ago. So let me start with now it works. So briefly about us, we're a relatively young company located in the heart of Czech Republic, Brno. And there are a lot of people saying that Brno is the homeland of the electron microscopy in the world because it's around 30% of all the electron microscopes are produced in Brno. Many thanks goes to our friends, colleagues, and partners from Tescan, Orsay Holdings, and Thermo Fisher Scientific, and of course, DeLong Instruments. Plus to that, we are extremely grateful that we are surrounded by, first of all, such big players on the market of electron microscopes. And the second is that we are surrounded by so many universities, research institutes, and research centers, such as Masaryk University of Technology, Masaryk University, Brno University of Technology, Central European Institute of Technology, the one where I get my PhD title. All of those places, they work in a wide variety of scientific fields, such as material science, semiconductors, batteries, life science, of course. And the reason why we are so happy is that those places, they gave us, let's say, the ground where we could study and test our device, where we can be useful, where we, let's say, what part of our microscope we need to improve, and where should we go, let's say. So briefly, yeah, it's about that. And now we're coming to our product, LiteScope. As I said, it's a compact atomic force microscope module that can be easily installed. And on the photo, you can see that the LiteScope installed onto SEM stage of the Tescan microscope. And now you can see the video taken from the electron microscope directly. So here you can see that the atomic force microscope probe is scanning the powder particle in situ. In situ. So we can really study everything in case of the roughness. So now we're coming to the motivation point. Let's say why to have AFM inside of your SEM. Well, the reason for that is that both techniques, AFM and SEM, they're the mostly utilized techniques now when it comes to the point of analysis structures or surface topography or combination of electrical mechanical properties together with the surface topography. Therefore, we try to take the advantages from AFM side, such as precise sub-nanometer topographical analysis, measurement of electrical, mechanical, and magnetic properties, together with the advantages of the SEM, such as very high contrast, structural characterization, the surface modification done by focused ion beam or GIS system, and moreover, even the combination with the energy dispersive X-ray spectroscopy, giving us the distribution of the chemical elements over the surface. So all of that can be combined using the AFM and SEM technique, which we are promoting. Now coming to the point of exact benefits, why to use AFM and SEM technique. The first benefit is the in situ sample characterization. The second one is the correlative multimodal sample analysis. And the last one, but not the least, is the precise localization to the region of interest. So therefore, we're trying to provide information to the scientists which they otherwise wouldn't be able to obtain or to reach. So a bit in detail about the benefits. So in situ sample characterization, it means that all the measurements are done at the same time, at the same place, and under the same conditions. Since you have AFM inside of the SEM chamber, so you really have a control over the atmosphere that you have. You know exactly what do you study, and you know exactly where your AFM probe is. And why it is so important, it's just imagine that usually the AFM-in-SEM machines, they are not located in one rooms. Usually they are located in different rooms, different buildings, and sometimes even in different districts. It means that having the AFM inside of your SEM, you simply avoid the process of a sample transfer from one device to another. And moreover, or plus to that, you also avoid the contamination of the sample surface or its oxidation. Therefore, if your sample or if the surface of your sample is very sensitive to the atmosphere, well, the in situ measurements is the must for your research. And we are very proud about the words of our scientific ambassador, Mark-Georg Willinger, from Technical University Munich. He said that the LiteScope is like a Swiss army knife inside of your SEM, meaning that with one tool or with one device, you have plenty of tools that you can apply or in order to get the results that you want to have. The next benefit is the correlative multimodal analysis. It means that besides the standard 3D topography, which is provided by AFM, we can combine it together with the sample surface characterization, together with the mechanical properties, and together with the elemental distribution, thanks to the EDX. And as I said, all of that is done in situ, and you know exactly what do you study. And so, yep. The next benefit is the precise localization to the region of interest, meaning that we have the complete control over the measurements, meaning that on the video now you can see that the nanowire which are attached to the protein columns, and by my opinion, I really can't imagine how such measurements or how we can precisely navigate the AFM probe to the nanowire in the standard optical system and then to do the meaningful measurements. So, and many thanks goes to electron microscope and the electron beam that we can get a much higher resolution, and we can precisely navigate the atomic force probe without the risk of the damaging of the sample surface or of the AFM tip itself. Now I come to the point of the correlative microscopy performance together with the correlative probe and electron microscopy technique. So the measurements, how they are done, how we do the AFM-in-SEM measurement. So the sample is scanned simultaneously by electron beam and by the AFM tip, so that we can get the data from the secondary electrons or backscattered electrons detector and from AFM tip with the So, and then we can do subsequent data correlation inside of our software, which is provided, of course, with the product, etc. So, what I wanted to say that all the measurements are done simultaneously, so you're not spending twice time in order to measure firstly SEM and then to measure AFM and then to correlate it somewhere, but everything is done simultaneously in one software with one device. Moreover, since I'm also responsible for our customer success, and I'm I'm very proud about our progress in the user experience direction. So recently we have one of the steps that we have done so far. We were trying to improve the automatization process of the measurements so that our users, not all our users are very experienced with AFM devices. So even if the user is not experienced with the AFM, he can do perfect measurements. Therefore, we implemented automated tuning of the probe. and automated approach of the probe to the sample surface. What does it mean? In fact, it means that just after several clicks, in fact, there are just 3 clicks, we tune the probe, we find the resonance peak, or the software find it, then we press the button auto approach in order to reach the sample surface, and we can do the measurements right away. So, yep. So here you can see we can start the measurement, and we already have the topography performance. So everything to improve the life of our users or to make doing the research easier. And the next step of the user experience, well, everybody knows that different samples, they have different physical properties, and sometimes those physical properties do not match so much the interaction with the electron beam. And since we are taking data simultaneously from the AFM probe and the secondary or backscattered electron detector, and during the measurements, the sample is subjected to the electron beam, the interaction with the sample surface might lead to the effect, or so-called as electron beam drifted image. What does it mean in reality? It means that when you have the AFM image and the SEM can be just slightly shifted to the left, right, or under some certain angle. And in order to do the subsequent data correlation of the AFM and SEM data, we implemented already the artificial intellect, the so-called Nano AI, in order to do the automated data correlation inside of our software. And as the result, you can see here the perfectly matched SEM data lying over the amazing 3D topography. So now, finally, I can speak a little bit very briefly about the LiteScope itself, how the setup look like. All what we need is to have the computer, which is connected to the Wi-Fi. Then we have the control unit, which is called Nenobox, that can stay on the table. And this Nenobox controller connects to the computer is connected to the Wi-Fi of the Nenobox controller. Then using 2 cables via feed-through, we can connect the LiteScope itself, which is installed already in SEM chamber, to the control unit. So by simple calculation, we can say that it will require maybe 10 minutes maximum in order to install LiteScope inside of your SEM chamber, because in fact, what you need to do is just connect 2 cables and then connect 4 screws. So even if you spend 1 minute per each part of this step, it will not take you more than 10 minutes. So the easy plug and play process allows our users to install LiteScope within 10 minutes into the SEM chamber. They do their measurement, and then if they want to use the SEM in the standard regime, again, you just spend 5 to 7 minutes and remove or uninstall the LiteScope, and you can continue working. Moreover, you can even take the LiteScope and to bring it to another SEM and to do the measurements there. So this is where we are focused on with the easy plug and play solution. So since we are measuring not only surface topography, but also many other properties, we're using several 2 main, let's say, group of atomic AFM probes. The first one is the Akiyama-based self-sensing probes. We're not using any laser system in order to navigate or the AFM probe or to detect the changes in the topography, but the probe is in the tapping mode, the Akiyama-based. They're working in the tapping mode all the time, scanning the sample surface. So the standard Akiyama sensor is used for the topography measurement and qualitative mechanical analysis of mechanical properties. The upgraded Akiyama probe with the magnetic wire on the end is used for measurement of magnetic properties. And the second group is the piezoresistive based probes, which are applied in order to measure electrical properties, surface charge by Kelvin probe force microscopy, piezoelectric effect done PFM technique, and of course mechanical properties. measured by force-to-distance spectroscopy. And as the accessory, we also created the additional nano-indentation module, thanks to our friends from Alemnis company. So we can install additional nano-indenter over the LiteScope AFM, so that, and all of that can be inside of the SEM chamber, so that you can do complete set of measurements done together with the SEM characterization and in situ. And in case of nano-indentation, we are using the Berkovich type. Coming to the, I believe, the most probably interesting part is the application areas. As I said, we are surrounded by so many nice research, nice and successful research groups and institutes. So we have plenty examples in application in different directions. And we decided to summarize them into 4 main groups, such as the standard material science or classic material science with the metal ceramic alloys, coming to the nanostructures and semiconductors. And I believe the most interesting for our current webinar is the life science, based on the pharmaceutical studies, the cell biology, marine biology, and many others. So I'm coming to the examples of the life science application. So the first example is the polysaccharide fiber. Everybody knows that it's a well-known material with the unique properties, unique mechanical properties that can be easily utilized in a biomedical or drug delivery application. In that case, the tricky part was to navigate the AFM probe to the area of interest, because the interest was to study the cross-cut section of the particular fiber. Therefore, the way how we did it, we firstly took the sample, cut it in half using focused ion beam technique in SEM. Then we tilted the sample surface under the certain angle, and we easily navigated the AFM probe to the particular fiber. And I'm sorry, my computer is not so fast. So yeah, we studied the AFM, we studied the sample surface by AFM tip, and we obtained very nice topographical image, or the height map distribution of the particular fiber. That's exactly what our customer needed. The next example is the analysis of the effect of depletion of YES-assisted protein on the mechanical properties of cells. Since it's important to understand the interaction between the cells and nanoparticles, several pristine cells were compared to the YAP depleted cells. The AFM-in-SEM technique was utilized successfully to find the area of interest. It means that we navigated the AFM probe to the particular or selected cells, depleted and the pristine. Then we performed the complex analysis, including the standard topography measurements, topography measurements, together with the structural characterization, together with the measurements of the mechanical properties, thanks to the force-to-distance curves technique, revealing that the YAP depleted cells possess much smaller young modulus and slightly higher surface roughness in comparison to the pristine cells. And the final results, as well as the deeper discussion of the research, were recently published in the Advanced Science Journal, and I believe it's in an open access right now, so everybody can read it and check it. The next example is the complex analysis of the artificial protein or spider silk nanowires. That's the example that was revealed on the video. So here thanks again to the unique properties of the spider silk nanowires and the high interest of their high interest in the biomedical application. However, currently there are all the, let's say, fabrication processes that are existing right now. They suffer from the reproducibility of mechanical properties of produced protein or spider silk nanowires. Therefore, in the current work, in the new production way was implemented that of recombination of the spider silk nanowires, and the task was to estimate the mechanical properties exactly, to know the mechanical properties of those nanowires. Therefore, using the AFM-in-SEM technique, so we firstly implemented the sample to the SEM, or to we established to the LiteScope, put it into the SEM chamber. We found the selected nanowires that we would like to study. We easily navigated AFM tip to those nanowires. And then, again, thanks to the force to distance spectroscopy technique, we were able to precisely measure or evaluate the tensile strength of the nanowires by simply pushing the AFM tip towards the nanowire until it got broken, as you can see on the graph on the right side. And again, the full article or the full research was published in the article together with the detailed description of the process, and it was published in the Macromolecular Bioscience Journal. However, I'm not sure about the open access so far. Yeah. And the last example is the study of stem cells on the surface of the scaffolds. The critical issue when you are studying the scaffolds by means of AFM is the impossibility to navigate and localize the AFM probe onto the surface of the scaffold, because the surface of because the scaffolds possess extremely high surface area and extremely high and complex surface area. However, using the AFM-in-SEM technique, again, we were easily able to find the point of interest, or let's say the attached stem cell on the surface of the collagen scaffold. So we did the study of its structural characterization together with the topography. And we, of course, also measured its mechanical properties, revealing that the stem cells possess plastic deformation, while the surrounding the scaffold revealed more elastic deformation type. So I think I have a bit more time, so I'll briefly pass through the measurement modes. So just to summarize, as the total, besides the standard combination of the AFM topography together with SEM characterization, we can also provide the measurement of mechanical properties done by tensile strength. Depends on the way how the sample is attached, of course. So we can measure tensile strength, we can provide measurements on the adhesion and on the stiffness. Plus to that, with additional nano-indentation module, the user or researcher, they also can study the nano hardness of their sample surface, of their sample or grains or cells. The next part is the measurement of electrical properties done or combined with the conductivity mapping, Kelvin probe force microscopy, and surface potential. Also, we can provide the electromechanical properties done by piezoelectric domain imaging, and of course, magnetic properties done by MFM performance. So thank you very much. That's all from my side. I think I matched the time that I had. Yeah. So if you have any questions, please let me know. I will just switch the slide because I don't like the group.